Hello, we're Group A, and today we're going to present you our Smart Mobility project. Our project is autonomous Arduino smart car that can move by itself, detect obstacles, and choose safer direction to avoid collisions. The main goal of this project was to understand how smart mobility systems work, using simple hardware and programming. Smart mobility means transportation systems that use technology to move more safely and efficiently. In our project, we use an Arduino-based robotic car with sensors, motors, and automatic decision maker. This car can move forward, detect obstacles in front, measure distance, look left and right, as well as choose the safer path and continue moving without human control. This project helps us learn both hardware connection and software programming. Today, our presentation will include project overview, hardware and code explanation, system logic, demonstration, and team member contributions. Now I'll pass the next member to hardware explanation.
I will explain the hardware components used in our project. The main controller of the smart car is Arduino Uno. Arduino Uno controls the whole system. We have used ultrasonic sensor to detect obstacles, and ultrasonic sensor can detect obstacles by sending waves. Also, it can measure time for sound to return. Servo motor used to rotate ultrasonic sensor, and servo motor can move the sensor in directions left, right, and center. The function of DC motors is to move a car, and we have used motor driver control because Arduino Uno cannot directly power the motors. So what does the motor driver do? It controls motors safely. In our project, we have used 4 infrared sensors because they can detect surfaces and nearby objects. So the main purpose of this smart car is autonomous movement and obstacle detection.
So in this part, I am going to explain the coding. The actual codes that we wrote to run our Arduino car. So before we dive into our code and all the files, let me introduce and give some snapshots about the overall architecture and system. So here you can see our design for the AEB, after emergency braking. So here we start the system, set up the ultrasonic sensor pins, set up the motor pins, set up the serial communication as it goes, and we have sort of print. There's a message on the screen that says AEB system initialized, and the loop starts. And then what happens is there is a couple of functions. So namely get distance, trigger pin, and low to ms, and trigger pin high, trigger pin low. So it changes, depends on the situation, and it reads the pulse duration, and it calculates the distance based on the constant value 0.0343 multiplied by half of the duration. That's how we can get the distance, and it returns us the distance. So after it prints the distance in the serial monitor, what happens next is, so it calculates if the distance between the object is 15 centimeter or less, it stops the car. As you can see, if it's yes, it stops the car, set the engines IN1, IN2, IN3, IN2 to low. So what happens if it's not? If it's the longer, so it keeps moving forward. As you can see, these two are the front and back motors, and their speed is 180. So, and then it waits for the 100 milliseconds, and loop, as you can see, continues. Otherwise, in this scenario, it prints the obstacle detected, it brakes, and wait for the another 1700 milliseconds, which is about 1.7 seconds. And it stops the car again to make sure that it really stopped. That's how the logic works in our program. So yeah, we are fully done with the flowchart, and let me move you to the coding part where the everything, including the magic, happens. Here is the coding part, autonomous emergency braking, and I'm gonna walk you through the explanations and what do is what here. So, in general, the system is designed to detect obstacles using ultrasonic sensor and automatically stop the car if something gets too close. Let's go through the code step by step. So we have three pin and echo pin here, A0 and A1. These are used for the ultrasonic sensor. The trick pins the sense out the signal and the echo pin receives the reflected signal. Next, we define motor drive pins. ENA and ENB are used for speed control and using PMV signals. IN1 and IN2 control motor A direction, and IN3 and IN4 controls the motor B. Then we declare two variables. Duration stores the time it takes for the ultrasonic signal to return, and the distance will store the calculated distance in centimeters. So, and their data type is float and long. So now we move to the setup function. In setup, we start serial communication at 9600 so we can print distance values to the serial monitor. Then we set the pin modes. The trick pin is an output and the echo pin is an input. So what happens here is that all motor pins are set as outputs because we control the motors directly. And at the end of the setup, what we do is we print a message saying that AB system initialized, so we know the system has started. Now let's look at the loop function, which runs continuously. First, we call the get distance function to measure how far an object is from the car, and then we print the distance to the serial monitor for debugging and observation purposes. Next is the key part of the AEB system. We check if the distance is less than or equal to 15 centimeters. If it is, that means that obstacle is very close. So we immediately stop the car by calling the stop car function. Also, we print a warning message, obstacle detected, braking. Then we add a short delay to ensure the car fully stops and does not move accidentally. If the distance is greater than the 15 centimeters, it's all simple. The car continues moving forward by calling the move forward function. At the end of the loop, we add a small delay of the 100 milliseconds to stabilize the readings. Now, let's examine how distance is calculated. If the in the get distance function, we first send the trigger pulse. We set the trig pin low briefly and then high for 10 microseconds and then low again. This sends an ultrasonic wave from the sensor. Then we use the pulse length function to measure how long it takes for the echo signal to return. Using this time, we calculate the distance with the formula. Distance equals to 0.0343 times the duration divided by 2. The division by 2 is because the signal travels to the object and back. Now let's look at the motor control functions. The move forward function sets the bus motors to move forward. We use the analog right with the value of 180 to control the speed. Then we set the direction pins so bus motors rotate forward. The stop car function is simple. It sets all motors control pins to low, which immediately stops the bus motors. So overall, the system continuously measures the distance in front of the car, and if an obstacle is detected within the 15 centimeters, it automatically stops to prevent the collision. This is a basic implementation of an autonomous emergency braking system, similar to what is used in real autonomous vehicles, but on a smaller scale using Arduino. Thank you for watching this explanation. And we move to the next part.
So, hello everyone. Today I will explain our Arduino obstacle avoiding robot car scenario of our project. So, my name is Samad Mirzahan, and let's get started. This robot car is designed to move automatically and avoid obstacles without human control. The main objective of this project is to demonstrate autonomous navigation using scenarios, motors, and Arduino programming. For this project, we used an Arduino board, an L200 98N motor driver, DC motors, ultrasonic sensor, servo motor, IR sensors, and robot chassis. Now I will explain how the system works. The robot automatically moves forward continuously, and an ultrasonic sensor is placed at the front of the car to measure the distance between the robot and the obstacle. The ultrasonic sensor works by sending ultrasonic sound waves and receiving the reflected waves. Using the travel time of the wave, the distance is calculated. In our code, the ultrasonic sensor trigger pin is connected to A0 and the echo pin is connected to A1. So we will see all of this as we continue explaining the code. We also use a servo motor connected to pin number 13. The servo motor rotates the ultrasonic sensor to the left and right sides of the robot, so the robot can scan the environment and decide which direction is safer. And for motor control, we use the L298N motor driver. The motor speed is controlled using PWM, which is pulse width modulation. In Arduino, PWM values range from 0 to 255. In our code, we use analog write ENA speed car, analog write ENB speed car. This controls the effective voltage supplied to the motors. I will explain this. I will also explain these parts during the code explanation. And the effective voltage formula is voltage equals voltage supplied multiplied by the PWM divided by 255. So by using this formula, we can control the speed of the robot smoothly. Now I will explain the main parts of the code. So let's get started. First of all, we included the servo H motor library for the servo motor. This and also we defined all the motor pins here, motor driver pins, IR sensor pins, ultrasonic sensor pins, and as I told you, we put the uh, trigger equal to A0, echo pin equal to A1, and we created a servo object called scanner. Here you can see, and servo pin is set to be equal to 13, and inside the we have some variables here inside here in the code: distance forward, distance left, distance right, and also the speed of the car is being put to be equal to 200. And here we have the setup loop. So inside the setup function, we initialize serial communication, configure all pins as input or output, and attach servo motor. And the servo initially moves the center position at 90 degrees. Here you can see scanner right 90. It's like right. It's written like here. And now the most important part is the loop function. Uh, like we have a main loop over here, and inside the loop, robot continuously measures the front distance using the read distance function. In the front distance, like in the front distance, if the distance is greater than 30 centimeters, the robot moves forward, as you can see here, which means the path is clear. And if the if an object if an obstacle is detected closer than 30 centimeters, the robot stops first, then slightly moves backward for safety. Here is, as you can see, it's like backward, stops motors, And then after that, the servo rotates left, measures the left distance, looks left here as we define it, measures the left distance, gets the distance, and then it rotates right and measures the right distance, and the same thing for the right side of the car. And the robot compares both distances. So in order to make a decision to which path to go, and if both sides are open, it chooses the side with more free space. Both sides are open, like distance left greater than 30, distance right greater than 30. If the distance left is greater than the distance right, it goes left. Uh, if it's like instead right distance is right, I mean the right side, the space in the right side is greater than the space in the left side, then the robot goes to the left side. uh, if both sides are open, it like as I told you, like it compares. If both sides are blocked, the robot moves forward. No, sorry. So the robot moves backward and turns around to escape the obstacle. So here both blocked, backward, and like then uh, the robot turns around to escape the obstacle. Now I will briefly explain the movement function. So distance function over here. The forward function rotates both directions, both motors in forward direction, and the backward function rotates both motors in the like here backward direction, right side, left side, like, and also the left function rotates the left wheels and the backward direct left backward and the right wheels forward, allowing the robot to turn left. Similarly, the right function turns the robot right. Finally, the stop motors function stops all of the motors. And yeah, that's like all of the functions of our robot given by the code. And overall, this project demonstrates autonomous obstacle avoidance, sensor integration, PWM speed control, and motor control using Arduino. So that's pretty much about our project's obstacle avoiding scenario. So thank you for listening. That's all.
Hello, I will explain the decision-making logic of our team's smart car. This is the most important part of the project. First, the ultrasonic sensor. It checks the front distance. If the distance is 30 centimeters or greater, the path is considered clear. The car moves forward. If a object is detected within the 30 centimeters, then the following steps happen. Step 1, stop the car. Step 2, move backwards slightly. This creates space for the turning. Step 3, the servo turns left to gauge the distance. Then it turns right to gauge the distance on the right as well. Step 5, the servo turns to the center. Then the car makes a decision. Case 1, both sides are clear. Here, that our car chooses one with more free space. Case number 2, the only left side is open, so the car turns right. Left. Case number 3, only the right side is open, so we turn right. Case number 4, both sides are blocked. In that case, we move backwards, then rotate tight. This logic simulates simple automation driving behavior. The car can react without human control. This is a basic mobility detection system. Now, next people will explain the movement functions.
I will explain the motor movements, functions, and the teamwork. Our program includes separate movement functions, and this makes the program more clear and easier to code. And the functions includes forward, backward, right and left, and stop motors. And when you want to go forward, the both sides of the motors will go forward, and you want to go back. And for the turning, both sides of the motors will turn differently, which will make the machine turn, and this creates rotation. And we also used VWM motor control, which made the motor speed smoother. And for the team roles, team member 1 took the introduction and planning. Team member 1 took the introduction and planning. Team member 2 took the mechanical assembly, and team member 3 took the sensor testing. Team member 4 took the code integration. Team member 5 took the decision and logic. And team member 5 took the motor control and teamwork. And team member 7 took the conclusion and video editing presentation. And this project included both mechanical engineering and software engineering, and our team worked together very hard. And now on to the last member, they will conclude.
So before I will go to conclusion part, I would like to mention some major problems we had during our project implementation. So the first problem is that we switched 3 Arduinos because 2 of them were broken or were not working. And the second problem is that we accidentally blew up the motor shield component, so we had to replace it. And the last problem is that our Bluetooth sensor is not working properly. The device is not being detected by any other device, like our laptop or our smartphones. So because deadline was really close, we couldn't implement the Bluetooth to our project. So now let's move on to conclusion. This smart car demonstrates a simple autonomous mobility system. Our project combines sensing, decision-making, movement control, and obstacle avoidance. So our car can detect obstacles, scan surroundings, and choose a safest path automatically. Through this project, we learned Arduino programming using C++ and Arduino IDE, sensor integrations like ultrasonic sensor, Bluetooth sensor, infrared sensors, and motor control. We now know how to work with motors, like how to combine them together. We had 4 motors, and 2 of them are responsible for moving, for rotating only front side, and other 2 are responsible for rotating the back side. We had some we had some coding errors, so we were faced to debug them. So now we know how to debug the Arduino code as well. And through this project, we learned teamwork, like how to communicate with different people and how to make a good project with different skills. So because deadline is super close, I think in the future we could make some improvements, like we will make line following car, we will add Bluetooth remote control camera and camera-based object detection, GPS navigation, and of course AI decision making is also possible. Thanks for watching.